All right. So on Wednesday, we looked at this reaction. So we looked at two reactions on Wednesday where we add molecules to a carbon-carbon double bond. This is the reverse of the elimination reaction, right? If you went from the tert-butyl bromide to the alkene and HBr, that would be an E1 elimination. So that would be chapter 7. And the way this reaction works, the alkene is going to act as a base. HBr is going to act as an acid. We're going to protonate the alkene, get a carbocation. Right? So alkene acts as a base. That H can only bond to one of the two carbons. So if the two pi electrons are used to make a bond to an H, as a basic electron pair, and when one of those carbons can be bonded to H, that's going to leave one of the carbons positive. Right? Again, the reverse of this, I'll just write this above there. The reverse of this process is the E1 elimination from chapter 7. So this is addition of HX, Markovnikov addition. And then the last step of this addition is the bromide adding in there. So in principle, you already know this reaction. Right? Every year when I tell students this, hey, you already know this reaction, you guys don't like that because it's the reverse of a reaction you already know. But you do, I mean, it should be pretty easy to pick this up. So this is going to be, other things we did, this is going to be called the Markovnikov product. Because it follows what's called Markovnikov's rule. So the book gives you Markovnikov's rule as that when you add HX, that H goes on the least substituted carbon and the X on the most substituted carbon. That's not technically true. A better way to think about Markovnikov's rule is what I've written in red there, that when a reaction goes through a carbocation, it's always going to go through the most stable carbocation, right? And so if a reaction, if an intermediate in the reaction is a carbocation, and it's possible to make more than one cation, you're going to make the one that's most stable. So for example here, as an example of what I'm talking about, right? When this alkene reacts to bond to the H, that H has to go on one of the two carbons. H can only bond to one atom. So those two electrons in the pi bond are going to become a sigma bond to the H. And that H can either go here on the less substituted carbon or here on the more substituted carbon. If it goes on the more substituted carbon, we get a primary cation. If the H goes on the less substituted carbon, we get a tertiary cation. Right? Tertiary cation is more stable, so that's the one we get. In all the reactions in chapter 8 that go through cations that involve this electrophilic addition, we're going to follow this rule. All right? But there's also, anytime we have a way to do a reaction that we can do, right? So if we add HBr to an alkene, using the reaction at the top. If we just do a simple addition of HBr, we get the Markovnikov product. Sometimes you might want the anti-Markovnikov product, right? Having the bromide be on the other carbon. And so here, I'm going to put up how we do this. Usually heat.
But if you added heat, wouldn't you favor the elimination reaction?
Here, no. It's heat or light. You just need, and when I say heat, again, it's not like hot, not like 100 degrees. What you have to do here so the ROOR is a peroxide. The OO bond is called a peroxide bond. You guys know peroxides as H2O2, right? So hydrogen peroxide, you put it on your scabs and stuff, cuts. The reason you do that, that OO bond breaks, you get 2 hydroxyl radicals. Hydroxyl radicals are really toxic. But you make a small enough amount of them, they're not going to kill you. But if there's bacteria there, they'll kill the bacteria. Right? So if you do this reaction, I'm not going to require that you guys know the mechanism of this reaction, but you're going to have to know that if you do HX and you add a peroxide, you get the anti-Markovnikov addition. Right? There's only 2 ways to add HX to the double bond. Right? The H on one carbon, the X on the other, or you flip it around. So if you put a peroxide in this reaction, you're going to get the anti-Markovnikov product. And like I said, I'm not gonna make you know the. Sorry. You don't have to know the mechanism. Yeesh. But this goes through a radical. We're going to talk about radicals in more detail in chapter 10, sort of the last thing we do before Thanksgiving. I guess this is as good a time as any to tell you, so I put this in an email or at one of the announcements. Exam 3 will be 7, 8, and 9, so 7 is going to appear again on an exam. 8 and 9 are kind of related to 7, the way this reaction is. Chapter 10 will be on there, but we're only going to do a couple of sections on it. I keep telling people I'm going to get the sections up there. Chapter 10 is radical chemistry. I don't do a ton with radical chemistry, but we'll look at one reaction in particular that's important. But you should know, so a carbon-centered radical, right? This carbon here has 3 bonds, that's 6 electrons, and then a single electron. Okay, so the carbon has 4 valence electrons, minus 3, half of the 6 that it shares, minus 1. So it's neutral. And this, again, often students think of neutral things as being stable. This atom doesn't have a full octet. So it's electron deficient. Carbon-centered radicals are really highly reactive. Okay, so this reaction, the reason that this reaction gives you the anti-Markovnikov product is the mechanism doesn't go through a carbocation. The mechanism starts with a bromine radical adding to the double bond. All right, so it's going to add in such a way that we get the more stable radical. All right, the Br will add on the less substituted carbon. That'll give us a tertiary radical. If it added the other way, we'd get a primary radical. Radical stability, because that radical doesn't have a full octet. It's electron deficient. Its cations are also electron deficient. So radical stability mirrors cation stability. So anytime, if I ask you, or if Wiley Plotz asks you, or if an exam asks you to rank radical stability, just treat it like a cation. You guys can do that at this point. It follows directly. Okay, so like I said, I'm not going to ask you to draw this mechanism on a quiz or an exam, but I will ask you to know the reaction. And that's sort of going to be how all these reactions go. We're gonna look at a bunch of reactions that go through, they give you a Markovnikov addition reaction, and there's always gonna be this anti-Markovnikov way to do the same reaction. For example,
So, sorry, but really quick, so do you need a peroxide to get the Markovnikov?
yeah,
Anti-Markovnikov?
yeah, if you don't have the peroxide, right, it's just a reaction up above.
Yeah.
So you get, HBO, HX, no peroxide, you get the Markovnikov product, HX and a peroxide, you get the anti-Markov. So here's another reaction we did on Wednesday. And this is really the same, this is exactly the same thing we just did with HX. Right? The reverse of the HX addition is an E1 elimination. The reverse of the reaction I just put up here is the acid catalyzed dehydration we did, an E1 elimination of water that we did in chapter 7. All right, so H3O is a catalyst. You can think of what's being added here as being HX, right? H and X in this case is OH. You've got to have a catalyst in here. The alkene could just grab an H, you'd get hydroxide, right? So you'd be making a carbocation, which is a strong acid, and hydroxide, which is a strong base. And reactions are never going to make both a strong acid and base at the same time. So this reaction mirrors the acid catalyzed dehydration. Right, so you protonate the double bond just the same way you do over here with HBr. And again, you're going to make the more stable carbocation, tertiary. We're going to have water. Water is going to add to the cation. Again, water is going to add, not hydroxide. We're working under acidic conditions. You're not going to have a significant concentration of hydroxide if you've got an aqueous solution. So you need to bring in both hydrogens with that. And then you're working with water as a solvent here. So water will take that proton and give you the alcohol. And again, the intermediates for the reverse process the intermediates are exactly the same intermediates you have for the reverse process, right? In chapter 7, if I'd given you an alcohol and an acid, you'd protonate the OH, you'd get a protonated alcohol, water would leave, you'd get a cation, and then water would take a beta hydrogen, you'd get an alkene. Okay? So this is just what I've shown, the acid catalyzed hydration of the alkene, just the reverse of the reaction you know from chapter 7. And again, you get a Markovnikov addition. As Martin pointed out earlier, where to write it really. In the addition of HX, so water, HBr, HCl, whatever, heat's going to favor the elimination, low temperature will favor the addition. We talked about that too in chapter 7. And then the other thing is Le Chatelier's principle. Le Chatelier's principle to favor one side or the other. So in the addition of water, if we use excess water, right? If I use water as a solvent, water as a reagent, it'll push the reaction right. If I remove water, I boil it off, I put a drying agent in, I have it react with something, that'll pull the reaction back left. Right? So Le Chatelier's principle always, the principle tells you if you perturb an equilibrium, the reaction shifts to sort of compensate for that, right? So if I have a large excess of water, water will get consumed. If I don't have much water, if I have a deficit of water, or if water gets pulled out of the reaction somehow, the reaction will shift back, elimination.
I was just going to ask about the first step of the mechanism. So you're bringing a hydrogen and getting rid of a bond? Is that what's happening?
Yeah, I'm shorthanding that, right? So, and I didn't finish the rest of it. So you have H3O plus there. Right, the alkene's grabbing a proton, kicking electrons onto the oxygen. That gives us water. In this last step, H2O takes a proton, so we actually generate H3O plus in that last step. And that's why it's a catalyst, right? So it's consumed and it's produced. It's net, not there.
Okay. Thank you.
Yep. All right. The other thing, there's a couple of different things we got to consider here. One is, the next thing ought to be obvious, right? So H3O plus in water gives you Markovnikov addition of water. Just like over here, we want to be able to do an anti-Markovnikov addition, right? Synthetic chemists are going to want to be able to make all the different possibilities. If you become a chemist and you dig into the literature and you find there's this reaction that makes, you could make 4 different things, but we only know how to make 2 of those things, a surefire, easy way to get your name on a paper and get some grant money is to figure out how to make the other 2 things. That's true largely in science. Science is both an industry and a school of thought. So the scientific method, a rational way to test ideas, that's important. But science also, like the business of science, is figuring out how to give us more options. So if you look at a field and there's something that's easy to do, or not easy to do, something we know how to do, but there's something complementary that we don't know how to do, if you can figure that out, there'll almost certainly be a market, because there's already a market for that first thing. Right? Okay. So how do we do an anti-Markovnikov addition of H2O? So this is and I'm going to be abbreviating Markovnikov as Mark. I've always thought Markovnikov would make a nice name for a kid. Because, I don't know, my name is Paul Jones, right? People look at me funny when I check into hotels. They think it's a fake name. It's just as boring. So I figure, sometimes, there were times in my life I'd like to have a crazier name. I figure if you get a name like Markovnikov, if you grow up to be a drummer, you can be Markovnikov. If you grow up to be an accountant, you can be Mark. Like you can give a kid some options. I don't know, that's my way of trying to get you guys to remember this name. So, if you want to do anti-Markovnikov addition of water, there's not really this you can't do it with a peroxide. And so the way this works, let me put it up and then I'll try to explain it. You're not going to have to know this mechanism either, okay? So the reagents you use are borane, BH3. I'll talk about borane a little bit here in a minute. And then second, remember these numbers. So first you treat with borane, and then you treat with basic peroxide. And the product you get H and the OH go on syn. They go on the same side. So if this was done on a ring, you'd get a cis product, or you'd get the H and the OH cis on the ring. And it's anti-Markovnikov, right? So the H has gone on the more substituted carbon, the OH on the less substituted carbon. If this went through a carbocation, it would have had to go through the primary carbocation. Right? So Markovnikov's rule tells us the reaction that goes through a carbocation will go through the more stable carbocation. So what that means is this reaction did not go through a carbocation. And what happens here, this is one, I'll tell you why I don't. And so, I'll eventually finish the sentence. This reaction doesn't require BH3. It requires a BH bond. So you need a neutral boron bonded to an H. These things can be whatever. And actually, you get better selectivity for the anti-Markovnikov product the bigger those groups are. So some of this is directed by sterics. But the other bit that helps here, the BH bond is polarized the reverse of what you're used to seeing. So all through general chemistry, through most of organic chemistry, when you see a hydrogen on a molecule, you should think it's going to be partial positive or neutral. Right? A CH bond is pretty much nonpolar. H bonded to O or Cl. What else does it bond to? Nitrogen, sulfur, phosphorus, bromine, iodine. The H is always the partial positive. It's the less electronegative element. It's the partial positive bit. When it's bonded to boron, the H is actually partial negative. All right, so here, the partial negative hydrogen's actually adding to the carbon that would be the better carbocation. However, this reaction doesn't really go through a free carbocation. This reaction does, right, the pi electron, this reaction fits into this chapter because the pi electrons attack the electron deficient boron. A neutral boron has 6 electrons, so it doesn't have a full octet. So even though it's neutral, it really would like a couple more electrons. Right? The electron configuration will be more stable if that boron is negative. And here in a minute, we'll see a reagent that has a negative boron.
What did you say? Boron has 6 electrons?
A neutral boron. 3 bonds. Right?
Doesn't it have 5?
Yeah, there's 3 available. 3 and 2. 1 S2, 2 S1, 2 P2. So there's 3 electrons in the valence shell.
Yeah.
Right. So.
Oh, you're talking about it in the compound.
Yeah.
Oh,
It's sharing 6 electrons. Yeah. Okay. So the valence number for boron is 3. So if it makes 3 bonds, it's got to have the 6 electrons. Yeah. So, but it doesn't have a full octet. So the pi electrons attack the electrophilic boron. And again, this is not, you're not going to have to draw this mechanism. The H basically, the BH adds across that double bond simultaneously. It's a concerted process. So you never have the free carbocation. But the two things, the electronics of the BH bond, the polarity of the BH bond, and the sterics, right? The more sterically hindered position is going to grab the H, the boron, especially if you put groups on that boron that have a lot of steric bulk, we're going to less sterically hindered position. This gives us the product of step 1 is this. For BH3, each of those BHs can then go on and then add to something else. And then step 2, this mechanism is in the book. I'm not even going to begin to describe it. It's wild. It's not that I don't think you can get it. You can certainly read it. I think you can follow it. I try to keep, this is an organic chemistry class, right? So I try to keep things focused on the organic reactions, the reactions of carbon molecules. The BO bond, BO chemistry is quite weird. Anyway, so it's a strange, complicated mechanism. I try to keep you guys, I want to keep you guys focused on mechanisms where the thing with electrons donates them to the thing that doesn't have electrons. Lewis acid-base reactions. And the boron-oxygen chemistry gets pretty wild. So look at it, if you like mechanisms, this mechanism is in the book. But if you don't, you just want to memorize it, feel free to do that too. All right, so there you go. So the top board on each panel we did on Wednesday. So if you treat an alkene with HBr, just HBr, or just HCl, or just HI, the H is going to add to the less substituted carbon, the I or the Br or the Cl to the more substituted carbon. If you put that HX in there with a peroxide, and again, the peroxide can be basically any OO bond. Hydrogen peroxide, very often we use benzoyl peroxide. That's in a lot of skincare products. You can use T-butyl peroxide. That OO bond, it seems weird, but the OO bond is extremely weak. And so it breaks really easily. Sunlight, room light will break that bond. And then you get a radical, and then you get this chain process. Like I said, we will look at radicals in chapter 10 a little bit. If you have the peroxide in there, you add your HX in an anti-Markovnikov fashion. So you need to know Markovnikov's rule and be able to identify the Markovnikov product. If you can do that, you're always going to be able to come up with the anti-Markovnikov product. Just switch the two things that add. Right? If you can figure out my X and my Y adds this way to give the Markovnikov product, switch where X and Y are, that's your anti-Markovnikov product. For water, if you add water across an alkene with an acid catalyst, you'll get the Markovnikov product. And the other thing I should say here is, you can also add alcohols this way, so it doesn't have to be water. You could add an alcohol that way. To do an anti-Markovnikov addition of water, you're going to use a borane of some sort first, treat your alkene with that, follow it up with hydrogen peroxide and base. Stop the camera for a minute.